All right. So after completing the section on DC to DC converters, so let's do an application of these DC to DC converters in DC motor drives. So why DC motor drives? So the basic advantage is that the control system is easy in DC motors. So controlling DC motor is easy compared to others. So we can deliver high starting torque, as we can see in the case of electric trains. So they have a high starting torque. So that's also a benefit of a DC motor. So they have almost linear performance, a linear mode of operation. So what are the disadvantages? High maintenance is required in case of DC motors. They are expensive compared to induction motors, which are quite low cost compared to this. So for high speed, they are not very suitable due to the use of commutators and brushes, because of the wears and tears of commutators and brushes. So in clean environment also, they are not very suitable. So now what about the DC motor drives? After getting to know about the advantages and disadvantages of DC motors. The DC drives are relatively simple and low cost compared to the induction motor drives. But we know that DC motors are comparatively expensive compared to induction motor drives, as we know. And due to these several disadvantages of DC motor, especially the maintenance costs, these kind of motors, DC motors, are not popular anymore in high power applications. So for low power applications or medium power applications, they are still economical, including the cost of the drives, because the cost of drive is very, very low cost in case of DC motors compared to the others. And for servo applications, these DC drives are still popular because of the better dynamic response. And we know they are easy to control. So the control system is not very complex. So still not popular for high power. Okay, so now we know that, okay, the advantages of DC motor drives, even disadvantages also, but we'll be talking about the advantages. Because of these advantages, these DC motor drives are still popular in industry for low and medium power applications. Using this equation, the instantaneous field current, we can easily find out the instantaneous field current in this particular DC motor, where we have the voltage across field resistance and voltage across field inductance. And getting to know about the voltages across field resistor and inductor, we can find out the instantaneous value of field current. Same way, we can find out the instantaneous value of armature current using this equation. And here we have the back EMF generated by the motor. So this back EMF, which is also known as a speed voltage, because of the movement, the back EMF is generated, which is expressed as this equation, the back EMF equal to kV omega IF. This kV is a constant known as motor voltage constant. And this omega is the motor speed. And IF is the field current. So the back EMF is dependent upon the speed of the motor and the field current. So now, after we get to know about the values or equations of these field and armature voltages and currents, so how to use these DC drives to operate these motors, DC motors. And we have seen the switched mode DC drives give us lossless operation, ideally. So we'll be using switch mode DC drives, as we have already discussed in section 5. So we know that supply is DC, so we can use DC to DC converter. So in this case, these DC to DC converters can be used for applications where we require position control, slow or fast response depending upon our requirement, such as servo applications or robotic applications. And we know that DC to DC converters, the switches can operate at very high frequencies, kilohertz to megahertz. So the average output voltage response is significantly faster. So the armature current ripple is then comparatively less compared to the controlled rectifier, as we have already seen in DC to DC converters case. So while designing DC to DC converter, we can select the values of all these parameters: inductance, capacitance, maximum value of coil current, minimum value of coil current, so, and the switching frequency, of course. So just by optimally deciding these values, we can easily get a less than 1% of ripple. We saw that we did one example based on that. So designing those values for all these parameters and components, we can get less than 1% of ripple at the output. So we can use the benefits of high frequency or high switching frequency to remove the ripples. So in that case, we'll be talking about quadrants of operation. So in this particular application, we'll be talking about 3 possible configurations where we can have a single quadrant operation, 2 quadrant operation, and 4 quadrant operation. So what are these quadrants of operation? So we know this first quadrant. On this graph over here, on x-axis we have a speed of a motor, on y-axis we have a torque. And in this first quadrant, we have a forward motoring configuration. So we configure this application in forward motoring in first quadrant. So this will be an equivalent circuit if this motor is operating in first quadrant. Now about the second quadrant, this is forward generating mode of operation. And the equivalent circuit is this. And in quadrant 3, we have a reverse motoring configuration. And the equivalent circuit is this. The negative of the DC supply is connected to the negative of the motor, of the EMF, back EMF. Quadrant 4 is reverse generating. And the equivalent circuit is this. So quadrant 1, forward motoring, and diagonally opposite to it is reverse motoring, quadrant 3. Similar is the case for forward generating in quadrant 2 and reverse generating diagonally opposite quadrant 4. So forward motoring, we have this current in positive, voltage in positive, torque in positive, and speed in positive. Quadrant 2, current goes negative, voltage remains positive, torque becomes negative, negative torque axis, and speed is positive. Now in quadrant 3, current goes negative, voltage also goes negative, voltage has a negative value, torque also has a negative value, speed also has a negative value. Reverse motoring, completely reverse compared to quadrant 1. And now completely reverse generating compared to quadrant 2 is current becomes positive, voltage becomes negative. Torque is now positive, speed is now negative. So we'll be using these quadrant of operations in this application. Okay. So for a single quadrant drive, in quadrant 1, where all parameters are positive, current, voltage, torque, and speed are all positive. So in this case, this is a circuit. This is a DC to DC converter simplified with just one switch. And this is the motor. And we have an armature current flowing in positive direction. So from time 0 to time period t, the armature voltage is at steady state, assuming it. So this armature voltage is an average of this voltage from 0 to t on when this switch is turned on. So during this switch, when this switch is turned on, the voltage given is by this pulse, which is V, this value, integrated from 0 to t on divided by total time period, which is t on plus t off. So now in this 0 to t on, the current starts to ramp up. And during t off, the current starts to ramp down or decay. So the armature voltage, the average voltage is equal to duty cycle, which is t on divided by t multiplied by V. Same we saw in the case of DC to DC converters. So this average armature voltage is equal to duty cycle multiplied by the voltage applied. This is voltage applied or input voltage. So now what about the average armature current? It is equal to the armature voltage minus the back EMF from the motor. So if it is 0, let's say ideally back EMF is 0. So VA is the armature voltage, RA is the armature resistance. So IA, the armature current, will be directly equal to armature voltage divided by the armature resistance. But we have this back EMF, so we can have a difference of armature voltage and back EMF motor divided by the armature resistance. That will be our armature current, which is shown by this waveform, which is ramping up during turn on of the switch, and during turn off, it is ramping down or decaying. And the speed, as we saw previously, can be approximated equal to VA divided by the constant, the motor constant, voltage constant, and the field current. Okay. Now forward motoring. If we connect this motor, instead of using single switch, we connect it with two switches, we can have two quadrants of operation. Here we were having only one quadrant of operation, only Q1, forward motoring only. And we get the average voltage, armature voltage over here, average armature current over here, and the speed. And these are the waveforms. But for two quadrant operation, we have forward motoring mode and a regeneration mode. So to start with, we go for a forward motoring mode, which is Q1. We saw that in here. So Q1 is a forward motoring mode. And this is a regeneration mode, a forward generation mode, quadrant 2. For forward motoring, T1, this is T1, transistor 1 or switch 1, and D2, diode D2. They operate. In this case, D1 is on. This transistor is turned on. So now this supply is connected to the motor through this switched on transistor 1. So the path of the current follows this path. So the motor runs through this switch T1 and so on. Now when T1 turns off, this supply is now disconnected with the motor through this T1 because it is turned off. T2 is already off. Diode D1 is reverse biased. So this armature current over here, which was flowing in first case through T1, will now follow this freewheeling path because all the switches are off. So this diode will freewheel the armature current through this, through D2. So we can easily find out the armature voltage across this motor terminal over here, which is this, by using a duty ratio, that for how long this switch is turned on, equal to T on, turn on time, divided by the total time period, which is T on plus T off. So just by using the duty cycle, or just by increasing or decreasing the turn on time of this T1, we can find out the value of VA, which is equal to dV. So VA will be calculated using this equation called dV, duty cycle multiplied by the supplied voltage. So that will be our armature voltage, 0 to T1, because for T off it is 0. So this will be the supply voltage here, connected in the negative and positive terminal over here. So armature voltage VA is equal to duty cycle D multiplied by the supplied voltage here. So that will be just determined by these two operations, T1 on and then T1 off. So just by switching on and off of this switch only, T1, we can operate this drive into Q1 mode or Q1 quadrant. So now if we want to operate this into Q2 quadrant, what we need to do is we need to operate T2 and D1. So we need to operate T2 and D1. So that is this one. So this T2 is switched on. So now the reverse current will start to flow through this motor to the battery, to the supply, DC supply input, because this switch is now turned on. So it is actually not working as a motor now, it is reversing its supply of current back to the input supply, back to the input battery. So it is supplying the current back into the battery. So now acting as a generator. So this motor is now acting as a generator, supplying back the energy. So now when T2 is turned off, this supplying back of the energy will follow through D1. This is D1, this. So supplying of the energy or current from the motor back into the supply through D1. So now this energy is being fed back into the battery or into the input through diode. So this motor is now regenerating, or in other words, it is acting as a generator. So it means quadrant 2, Q2 of operation will regenerate the energy back into the supply, back into the input voltage. So now moving further into 4-quadrant DC drive. So after this first quadrant and 2-quadrant drive, now we are dealing with the 4-quadrant DC drive. So to operate this motor into 4 quadrants, we need to have a circuit like this. So we need to have 4 switches, T1, T2, T3 and T4. So this will be our armature voltage over here. And the flow of the direction of the armature current will give us or will decide what quadrant this motor is working in. Okay. So now in first quadrant, forward motoring mode is the first quadrant, Q1. T1 and T2 operate, T3 and T4 are off. So T3 is off, so no flow of current. T4 is also off, no flow of current. Only T1 and T2 are on. So the supply of current, this current will follow this path. So now this input supply, DC supply, is now connected to the motor through T1 and T2 and back. So in this case, the armature current will ramp up. So in this case, the forward motoring mode, the armature current will ramp up, just like a inductive coil current ramping up. And here we have a inductance inside the motor. So this is an inductive load, RL load. You can easily say this can be an RL load. It has some resistance, field resistance or armature resistance, and field inductance and field and armature inductance. So this is a classical example of a RL load. Okay. Second, when T2 and T1 are now turned off. So now what happens is, this current, it was ramping up when T1 and T2 were on. Now after turning both of these transistors or switches off, the current will freewheel through D4 and D3 and it will follow this path, the opposite direction. So the current will follow the opposite direction, means the ramping up of the current will stop and now the current will ramp down. So in this case, the ramping down of the current will follow. So it means the current will decay. Next, when all these transistors T1, T3 and T2 all are off. Only T4 is turned on. So now the armature current, the current will follow this path from T4 and D2 and then through this armature and so on. So it starts to ramp up again in opposite direction. In this case, the ramping up was done in the forward direction from left to right, as shown by this arrow, in forward motoring mode. In regeneration or in quadrant 2, the current will follow the opposite path, and it is actually ramping up the current through T4 and D2. And now when T4 is also turned off, only D1 and D2 will start to freewheel the current in this direction because T4 is now turned off. So D2 was already conducting, and now with D2, D1 also starts to conduct. So now the current will try to flow back into the battery. So acting like a generator, supplying the energy back, which was ramped up during the previous cycle. Now reverse motoring. So in this case, T3 and T4 are turned on. T1 and T2 are turned off. So when T3 and T4 are turned on at the same time, simultaneously, the armature current again rises in this direction through T3 and back in reverse direction. In quadrant 1, this battery is connected through T1 and T2 and back. In quadrant 3, the battery is connected through T3 and back T4 and then. So the current reverses its direction of flow of current. So it reverses its direction. So the armature current ramps up in reverse direction. So in this case, the motor will rotate in reverse direction. So now this T3 and T4 are turned off. So when T3 and T4 are turned off, now the freewheeling action will start. And we know that freewheeling action will decay the current. So ramping down of the current. Whatever current was stored, or whatever current was ramping up in previous cycle, now the current starts to ramp down or current starts to decay through freewheeling diodes D2 and D1 in reverse direction again. So the motor will continue to run in reverse direction with falling current or with ramping down of the current. Now reverse generation. So after reverse motoring, we'll see how reverse generation will happen, means how this reverse current is transferring the energy back into the battery. So T1, T3 and T4 all are turned off. Only T2 is turned on. So when T2 is turned on, the armature current rises through T2 and D4 and follows this path, shown by the red arrows again. And the armature current follows the path from left to right. And now when T2 is also turned off, and now the freewheeling action starts. And this freewheeling action, we know will decay the current or will ramp down the current. So whatever current was, or whatever energy was stored in the armature is now starts to release through freewheeling diodes. So this current now follows this freewheeling path through D4, through this RL load, and then through D3, and then back into the supply. So this supply is now, so this energy stored in the armature is now fed back through D4 and D3 into the battery. So we can say that a single DC motor can be used in different quadrants just by deciding which switch out of T1, T2, T3, and T4, out of these four switches, which switch to turn on or off, or a combination of switching, plus which diodes are used to freewheel the current back into the supply. So just by changing the configuration of the combination of switches and diodes, we can decide which quadrant to operate this motor into. So very simple. So we can easily make a table out of it showing all these four quadrants, from forward motoring to reverse motoring, and then forward generation to reverse generation. And all these four quadrants, which switch combination is operated. And then based on that table, we can easily run this motor into all these four quadrants. So these are fixed configurations. And these fixed configurations can be put in tabular form. And based on this switch combination, we can decide which quadrant to work upon. So this procedure has to be understood, and you can easily make a table out of it. And then you can use this table just to run the DC motor in all four. These are fixed quadrants. These are fixed combinations of switches to find out which quadrant to work this motor in. So very simple.